Hello, my name is Jacob Cantor. I'm a second-year master's student here at Purdue. I am working currently at Fiat Chrysler Automotive in Michigan, and I'm going to present on the evaluation of 3D printers for use aboard the ISS, the International Space Station. So we're going to start off the presentation going over why this is important. We wanted to look at what reasons there might be. The main motivators here are time, money, and space, right? The average delivery to the space station takes about 2 weeks. As you can see on the figure to the right, they have scheduled deliveries every 14 days or so. Along with this time constraint, there's also an excessive delivery cost. With the article published by Business Insider and Washington Post, there is an estimated cost of $23,000 per kilogram delivered to the International Space Station. And not only is there this high cost to deliver parts to the space station, but there's a space limitation, right? You can only fit so much onto the space shuttles or the rocket launches taking parts to the space station, and there's only so much real estate aboard the space station. So to kind of get around this, we were wondering, what if we did manufacturing aboard the space station to use just-in-time manufacturing methods? This reduces waste in the transportation and the storage of parts needed. So to look into this further, we considered additive manufacturing. Now, the 3 different types of additive manufacturing looked at were stereolithography, fused deposition modeling, and selective laser sintering. Stereolithography works by laying down resin layer by layer. This resin works just like the glue that they put in your mouth when you go to the dentist. It's UV activated. So when the machine lays down the layer, it then runs a UV light over it at the specific parts to be hardened, and this solidifies that. This is good because it's accurate. And it's extremely repeatable. However, these parts are brittle, and there are fine particles produced by this resin. That's just a natural byproduct. The second method we looked at is fused deposition modeling. This method is most common. You've probably seen it at Best Buy, the MakerBots. This method works by using solid filament extrusions that are pushed through a heated extruder tip. These layers are then pressed together as they go on. As they cool, they harden and produce the final product. This is slightly lower accuracy, but the end result tends to be structurally rigid and allows for a large extrusion material. The third technique we'll be looking at is selective laser sintering. This method works by laying down resin layer by layer. Traditionally, it is a metal resin. It works quite similar to stereolithography in that fashion. However, instead of using UV light to solidify the resin, it uses lasers to actually melt the material together. This produces a mechanically strong part that is very accurate. However, there are additional fine particles produced as a byproduct of the process. So, when we wanted to evaluate these types, it was important to consider what characteristics were necessary, what physical and functional objectives it needed to perform. To break this down, it was taken to 3 categories of performance, interaction, and other. The performance category included that it had to be low weight because the mass and weight of the printer and material is critical in delivery to the space station. It needed to be high accuracy and high repeatability so that we got the parts designed that we wanted manufactured to spec. The last was quick print time. We want these parts to be printed quickly and efficiently so that the astronauts are not waiting days on end to get these parts. In interaction, we wanted these printers to accept multiple materials so that it could handle multiple physical properties. We wanted these printers to be serviceable so that if anything broke, they could be easily repaired. and we want them to have a small footprint so that they're not occupying too much real estate aboard the International Space Station. And the last category is other. This was cost. If the printers were too cost prohibitive, there would be no benefit over just shipping parts up in the traditional manner. So to evaluate these, we used a house of quality evaluation. This breaks down the customer requirements into engineering characteristics. These are then evaluated objectively so that we can determine the absolute best choice given our characteristics. Using this, the fused deposition modeling was shown to be the best pick. SLA and SLS methodologies were just behind. This is because the fused deposition modeling doesn't produce small particles, it's quick, it's robust, and it's low weight. So continuing on, we wanted to see what commercially available printers we might be able to use. Took the top 5 listed among a survey online. These included the Ultimaker 3 Extended, the Raise 3D N2 Plus, the Mark Forged Mark II Onyx, the Delta Wasp 4070 Industrial, and the MakerBot Replicator Z18. All of these are available under $15,000. They use fused deposition modeling methodologies, and they can be picked up on Amazon. So to evaluate these, we again use the house of quality, just taking this down one step from the technology side to the actual printer side. Using this technique, we found that the Ultimaker 3 was the best printer for the job because it was low weight, it was high accuracy, allowed multiple materials, and it was low cost. So then, to evaluate if this would actually work aboard the space station, had to do the cost analysis. As you can see, the cost analysis for shipping the part based on this $23,000 per kilogram up to the space station would be about $500,000 to get the Ultimaker 3 to the International Space Station. From the studies by Washington Post and Business Insider, it cost about $342,000 to support the International Space Station per hour. So if we could print one part that would keep mission critical functions running for more than 2 hours, the printer has already had a positive return on investment. To further assess this though, we wanted to consider what if you had to wait the full 2 weeks to get a part to deliver from Earth. What we imagine this is a ratcheting wrench, which they've actually printed up there in space as a test. This part took 10 hours to print, and we imagine that this would take 336 hours, or 2 full weeks to deliver. With these cost savings, there would be approximately $111 million saved by eliminating the lost time. So then continue on, we wanted to think about what future work might go on. It is important, we think, to actually validate these results in space, taking this to the next step and seeing if these commercially available printers will work inside this environment. The next thing is to actually improve upon the physical characteristics of the products. There are carbon fiber reinforced filaments that will improve upon the physical characteristics and produce products with much higher tensile strength. Another area of focus would be in satellite structure development. A unique aspect of printing in space is that the low gravity allows you to use structures requiring much less support than they would need if produced on Earth. We feel this is a great area to search and to try and improve upon. Thank you, and if there are any questions, I will be happy to answer them on Piazza.